Hi there. This is the video for lesson 6.1, Introduction to Vectors. So now that we have moved on from calculus, um, introduction vectors are very similar. If you have taken physics, grade 12 physics, maybe even grade 11 physics, you would have across vectors. Okay. So what exactly are vectors? Well, let's find out. It is, just to be clear, it does not really as a like in this course it's not going to feel like it's connected to calculus at all. Okay. Those connections will be made later on in university, but not in this course. So up until now you have dealt with quantities that are called scalars. Okay, so a scalar is just anything that has a magnitude or size. So speed, for example, height, cost of something, distance, acceleration, those are all examples of scalar values. What are vector values then? Well, vector quantity not only has magnitude, but has direction. Okay, so for example, if I took the speed, so 10 kilometers per hour, let's say, 10 kilometers per hour would be a scalar value. 10 kilometers per hour going north, that is now a vector. Okay, that would be what we call velocity. So velocity, acceleration, displacement, all those are examples of vector quantities because they have direction. Okay. Um, So for example, acceleration under scalars, I could be increasing, my speed could be increasing at 3 meters per second, so 3 meters per second squared. But my acceleration as a vector could be 3 meters per second squared going downwards. So a vector can be represented by an arrow called a directed line segment. Here are some examples of vectors. Yeah, so the first one we've got a displacement of 40 kilometers northwest. Okay, so northwest. Sorry, I think I opened it in the wrong. There we go. Northwest. Okay, so that's this example here. Okay, so this arrow that I drew is a vector. Okay, I'm not giving it an exact size, but it says it's a displacement of 40 kilometers. So I'm going to say this vector represents 40 kilometers going northwest. Northwest. Okay. B, we've got, oops, a weight of 900 newtons downwards. Okay, so that's an example of a vector. A velocity of 60 kilometers per hour going west. Those are all examples of vectors. Okay, so let's look at some notation. AB with a little arrow on top tells me it's a vector going from A to B, where the initial point is the tail and B is the terminal point. So A, B. So A, B, this would be an example of vector A, B. Okay. Another way to measure or label a vector would just be simply using a letter. Okay, so for example, I can say vector AB from A to B, I'm going to call this vector V. Okay, just for simplicity's sake, because later on we're going to be adding and subtracting vectors. So instead of writing vector AB, BC, etc., I can just call this vector V. Okay, so notation. If I put an absolute value, the absolute value sign around it, this tells me I'm talking about the magnitude. Okay, so for example, let's say I'm just going to make a number up. So let's say, you know what? I'm going to be revisiting example 1 in a second. Okay, so again, if I do this, talking about the same vector, I'm talking about the magnitude. Okay, now this absolute value is just to remind us that as with any absolute value, it should always be positive. So if we look at example 1a, that's this one, the magnitude of that vector, which we're just going to call v, is 40 kilometers because it was 40 kilometers. So if you look at the second one, the magnitude of this vector, which we just call v, the magnitude of that vector would be 900. Yeah, 900 newtons. And the magnitude of this vector would be 60 kilometers per hour. Okay, so let's draw a geometric vector with each bearing. So we want to draw a vector 4 kilometers. So you notice how there's no absolute value sign around it. So we want to draw the actual vector with a bearing of 295. So now this is where it gets confusing, especially after just finishing trig and calculus. Typically with trig, we would always start here, right? And go all the way around. Now, when we're talking about a bearing of 295, we're going to start at 0, which is going to be due north. 295, it goes all the way around starting from north. Okay, so now drawing a geometric vector with each bearing. So this vector needs to be 25 degrees going north west. Okay. How did I get 25? Well, 295. I'm told that this whole angle is 295, and I know that each quadrant is 90 degrees, right? So then I know that this is 90, 180, 270. So how far is 270 from 295? 25 degrees. Okay, next vector, vector u is 40 kilometers per hour at a quadrant bearing of south 70 degrees west. So south 70 degrees west, which means that green arrow represents 70 degrees, right? Which means that this little angle here is 20, because 70 plus 20 is 90 degrees. And the magnitude of this vector is 40 kilometers per hour. Now, translations can also be represented using vectors. So this rectangle ABCD, so A, B, C, D, okay, is said to be mapped onto the rectangle W, X, Y, and Z. W, X, Y, and Z. Okay, so it's being mapped from up to the top left to the bottom right. Okay, now this is going to be useful later on when we start working in 3D. Okay, so this mapping is represented by AW, BX, CY, and DZ. So AW is from A. Let's see if I can use the correct colors. So vector AW goes from A to W. Okay, vector BX, so that was blue, goes from B to X, and so forth. So those four vectors map the points A, B, C, D to W, X, Y, Z. When a shape or figure is translated, all points on the figures are moved in the same distance and in the same direction. Okay? The above vectors are the same magnitude and are in the same direction. So, what are equal vectors? We say two are said to be equal if, this is not a typo, IFF, it's just an easier way to say if and only if the magnitude of A is the same as B, okay, and vector A and B are in the same direction. Okay, so for example, let's call this vector A, let's call this vector B, let's say they are both 10 kilometers per hour. Let's just pretend we're talking about speed. Okay, those are equal vectors because they're in the same direction, same magnitude. If I all of a sudden did this, even though their magnitudes might be the same, 10 kilometers per hour, 10 kilometers per hour. Oh, this is terrible. They are not equal vectors, okay, because they're not in the same direction. Okay. So talking about inverse vectors, so we could write the inverse by mapping WA, which means that a point W is mapped onto point A. So for example, WA, AW. Okay, so those two vectors we can say are the inverses of each other. Okay, even though the magnitudes are the same, we can say vector AW is the same as the inverse of WA. Hence the negative sign. And then that's where we lead into opposite vectors. We say two vectors are opposite if the magnitudes are the same, but the vectors are in exact opposite directions. Okay. No, equal vectors need not be in the same location in space. A single vector can have an infinite number of representations. We'll talk about that later. Opposite vectors work in the same manner since they do not occupy the same location. Okay, so looking at here's an example, equivalent vectors. AB is equal to, so AB, vector AB, is the same as negative BA. And why is that? Well, what is BA? So BA technically is that vector, right? But BA as it stands, vector BA, is not the same as AB. They're in opposite directions. So to make them the same, I call it negative BA. So BA, but facing the other direction, which makes it the same as AB. Okay. Now it's also equal to DC, vector AB. Well, how? Well, here's vector AB, and here's vector DC. They're clearly the same magnitude and facing the same direction. Okay. So that's what we're looking for when we look for equivalent vectors. Opposite vectors, well, A, B, and C, D are opposite. Okay. How? Because AB is in that direction, but CD is in that direction, making them opposite. Okay. Okay. And that's pretty much it. This was more of a specific example, but we'll address that later. It's just talking about opposite vectors. Okay. Any questions? Of course, shoot me an email, and we'll chat soon.